This video, we're going to prove 5 facts about the greatest integer function. The first one we're going to work on is that for any integer n, the greatest integer of a plus n is just the greatest integer of a plus the number 1. If you like seeing mathematical proofs like this, you should consider subscribing to my channel, as that's all we do here. We prove mathematical theorems. So proof of A. Let me just write it down. The greatest integer of a plus n is equal to the greatest integer of a plus n, if in fact n is an integer. So this is what we want to prove. So how about we say that x is in between x and x plus 1. Whenever I talk about x and y, they're always integers for all 5 parts. Well, this by definition implies that the greatest integer of a is x. Okay? Now, how about I add n to both sides? So I get x plus n is less than or equal to a plus n, which is less than x plus n plus 1. Well, these are 2 consecutive integers. X is an integer, n is an integer. You add them, you get an integer. That tells me that the greatest integer of a plus n is x plus n. But there it is, I have it. The greatest integer of a plus n is equal to x. Just remember, x is the greatest integer of a. So this is equal to x plus n. That's exactly what we said. I just wrote x a little bit differently. That's the proof of A. The proof for B. Proof for B. Just to remind us, greatest integer of A plus the greatest integer of negative a is either 0 or negative 1. Let's just assume that a is greater than or equal to 0. That is, this is greater than or equal to 0, and that's less than or equal to 0. Okay. So a is in between 2 consecutive integers, might equal the lower one. This implies that the greatest integer of a is x. If I multiply everything by negative 1, I get this. This is a number, and that's 1 less. They're 2 consecutive numbers. That means this, the greatest integer of this, is equal to the smaller number. The greatest integer of negative a is equal to negative x minus 1. Now, I guess I left out something. Case 1. A is not an integer. A is not an integer. Okay, so the greatest integer of a plus the greatest integer of negative a. So what I can do is remove those 2 equality signs. Well, the greatest integer of a is x, plus the greatest integer of negative a is that, and that equals -1. Okay? That's case 1. Suppose case number 2. A is an integer. Well, in that case, the greatest integer of a is itself. And if a is an integer, negative a is an integer, and the greatest integer of the integer negative a is negative a. So we have the greatest integer of a plus the greatest integer of negative a. This one is a plus this one is negative a. We get 0. Only when a is an integer do we get this equaling to 0, and when a is not an integer, this is equal to -1. But I didn't have to show that. I just had to show that this is either equal to -1 or this is equal to 0. And that completes this proof. Well, I guess I should say combining both cases, we get that this sum is 0 or -1. Proof for C. C says that if A and B are positive, that the greatest integer of A times the greatest integer of B is less than the greatest integer of A times B. So that's what's given. Okay, so A is between x and x plus 1. By the way, x is at least 0. Why not bigger than 0? Well, if a is positive, but it's a small positive number, the greatest integer of it is 0. That is, 0.2 is in between those two numbers. Can equal the left one. Okay. So this tells us that the greatest integer of a is x, and a similar argument tells us the greatest integer of b is y. Multiplying those two results, we get that the greatest integer of a times the greatest integer of b is x times y. Okay, let's hold on to this. Let's call that equation 1. Now we multiply. We multiply those two, and we multiply AB. This is an integer. AB is greater than or equal to that integer. That implies that XY is less than or possibly equal to the greatest integer of AB. That's equation 2. Equation 1 says that this is equal to XY. Equation 2 tells us XY is less than the greatest integer of AB. Now let's just remove the middle. The greatest integer of A times the greatest integer of B is less than or equal to the greatest integer of AB. I mean, xy is less than the greatest integer of ab, and this is just another way of saying xy. That's why they're equal. They're equivalent. Okay, so that's the answer to part C. The proof of D. Well, D says that the greatest integer of a over n is equal to the greatest integer of a over n, greatest integer of that. And this is for n greater than or equal to 1. If n is 1, the greatest integer of a over 1 is just the greatest integer of a, because a over 1 is a. And this is equal to the greatest integer of a. It equals itself over 1. But now, since the greatest integer of a over 1 is an integer, and remember, the greatest integer of an integer is the integer itself. Doesn't matter what the integer is. So, since what I'm putting the greatest integer brackets around is an integer, I can do that. And the equality holds. So, what I have is combining or getting rid of the middle step. I have that this equals that. This implies that the greatest integer of a over 1 is the greatest integer of the greatest integer over n, which is 1. Okay. Now, suppose n is bigger than 1. N's an integer, but it is bigger than 1. Okay. So we know that a is in between x and x plus 1 for some integer x. Well, that implies that the greatest integer of a is x. Okay. Now, let me just write this down again. And I'm going to divide by n. This tells me that the greatest integer of x over n is less than or equal to the greatest integer of a over n, which is less than or equal to the integer of x plus 1 over n. Why all of a sudden the equality? Well, if you have the greatest integer of 1, well, let me start off without greatest integers. Clearly, 1.8 is less than 1.9. But the greatest integer of 1.8 and the greatest integer of 1.9, they both equal 1. Even though this number is less than that number, the greatest integer of those two numbers are in fact equal. So you can get equality. You're not going to get suddenly, you're not going to have 2.7 is less than 2.9, but the greatest integer of 2.7 is suddenly bigger than that. That you won't get. You might get less than or equal. You might get that. Like 2.7 is clearly less than 2.9. But the greatest integer of that, 2.7, is 2, while the greatest integer of 12.9 is 12. And clearly 2 is less than 12. But you can have equality. Okay, now, this is the same as x over n plus 1 over n. And that's the sum. That's less than the integer of x over n plus the integer of 1 over n. But if n is bigger than 1, that's a number, 1 over n is in between 0 and 1. That is, that equals 0. That equals 0. So what we have is that this here is in between x, the integer of x over n, and, the same thing, the integer of x over n. This implies that the integer, the greatest integer of a over n, is equal to the greatest integer of x over n. But we have a special way of writing x. It's the greatest integer of a, and then I divide by n. So this is equal to that. That is, the greatest integer of a over n is equal to the greatest integer of the greatest integer of a over n, when n is bigger than 1. Combining both cases, we have this equality when n is greater than or equal to 1. N is a positive integer. That finishes part D. Okay, part E, the proof of part E. Well, part E says that mn over k, the greatest integer of that is greater than or equal to m times the greatest integer of n over k. That's what I want to prove. Okay. And we're given that m, n, and k are all positive integers. Okay. So we know that n over k is in between x and x plus 1. This implies that the integer of n over k is equal to x. That implies that m times the greatest integer of n over k is equal to m times x. Why did I just say that? Because that's part of the problem. Okay. Now, if I multiply all three sides by m, what happens is, in the middle, I get what's in between those greatest integer brackets. This is less than mx plus m. Okay, so this is m more than this number, and m is an integer. This is not just one more. It might be 2 more or 22 more. So all I can say now is that mx is less than or equal to the greatest integer of m over k. Again, if this would have been mx plus 1, then I guarantee you that the greatest integer of that will equal mx. Or if the right left side was mx minus, or mx plus m minus 1. That is, it's 1 less than that. Then I can say that the greatest integer of this is that. but they're not. This number and this number do not differ by 1. Okay, so I get this inequality. Putting it together with this, I have m times the greatest integer of k is equal to mx. That's from here, and mx is less than or equal to mn over k. But that implies just what I want. You just don't say the middle step. What I just wrote is mx. It equals mx, which is less than mn over k, greatest integer. So that one is proven. The next one says that this will be the proof of f. It says that the greatest integer of a plus the greatest integer of b plus the greatest integer of a plus b, this is going to be less than or equal to the greatest integer of 2a plus the greatest integer of 2b. And we're going to have to do this one in 3 cases. Case 1 there is where theta and theta prime, which I haven't defined yet, are both between 0 and a half. So x, let's say a is equal to some integer plus a little bit more. So theta is less than 1. This tells me that the greatest integer of a is equal to, and I can do it in long form, it's equal to this, but that's an integer. And we actually proved in this video that that integer can just come out in front. Now, since this is between 0 and a half, this is 0. So that's x. And if we define b to be y plus theta prime, by symmetry, we get that the integer part of b is y. Now, just want to do some bookkeeping. To do this, we're going to need the integer part of a, the integer part of b, the integer part of a plus b, the integer part of 2a, and the integer part of 2b. Okay, integer part of a is x, of y is b. Now, let's add the two. A plus b is equal to x plus y plus theta prime. But if you add two positive numbers that are both less than a half, you'll get a number between 0 and 1. This here is in between 0 and 1. That means the greatest integer part of this is 0. So the greatest integer of a plus b is equal to the greatest integer of this. But xy is an integer. So plus the integer part of theta plus theta prime. But that's 0. And I do have a typo. It should be x plus y. Just like it was directly above. X plus y. Okay, so x plus y. So now let's talk about 2a. If a is equal to this, 2a will equal to 2x plus 2 theta. Well, if theta is in between 0 and a half, multiplying all three sides by 2, you get that 2 theta is in between 0 and 1. And twice an integer is an integer. So the integer part of 2a is the integer part of that. But since 2x is an integer, you get 2x plus the integer part of 2 theta. But that's 0, because theta is positive and less than 1. So this is 2x. And the b and the y, they're symmetrical. Okay, the integer part, the greatest integer of this, since that's an integer, it stays, plus the greatest integer of 2 times theta prime. But 2 times theta prime is between 0 and 1. We know that theta prime is in between 0 and a half. We double all sides. Double 0, you still get 0. Double a half, you get 1. 2 theta prime is jammed between 0 and 1, and it's less than 1. That is, this piece here is 0. So we get 2y. So we have 2x and 2y. And what we want to see is whether or not the integer part of a plus the integer part of b plus the integer part of a plus b, if it's less than the integer part of 2a plus the integer part of 2b. Now, the integer part of a is x plus y plus x plus y. So if and only if this is less than 2x plus 2y. And they are, because this is 2x plus 2y, and this is 2x plus 2y, so they're equal. And you can say less than equal. Somebody asked you, is 12 less than or equal to 12? You should say yes, because it's an or statement. 12 is less than or equal to 12. You just have to say that it's true for one of them to put the yes. I mean, it's definitely better to say 12 equals 12. Okay, that was case 1, where both theta and theta prime were less than 1. Now, case 2 will be where, say, only one of the thetas are bigger than a half. Theta or equal to a half. Theta prime will be between a half and 1. This means that multiplying both sides by 2, we have that. Multiplying both sides by 2, we have this. Okay, and once again, we're going to need the greatest integer of a and b, and of their sum, and of 2a, and the greatest integer of 2b. Okay. Now, we know that a is equal to x plus theta. But theta is between 0 and a half. And x is an integer. This implies the greatest integer of a is equal to just x. Or you can pull the x out in front, and theta remains inside the greatest integer. But this is 0, so you get x. B is equal to y plus theta, but theta prime is positive and less than 1. That means the greatest integer of theta prime is also 1. So this implies that the greatest integer of b is equal to the greatest integer of y plus theta prime, but since y is an integer, it can come out in front. But again, that's 0. Okay, so we have two of the results, x and y. Now, let's add them. A plus b is equal to x plus y plus theta prime. Well, let's be careful here. We know that theta is in between 0 and a half, and we know that theta prime is in between a half and 1. So if you add them, you get the following. Okay. So if you have a number, here's 0 and 1 and 2, you have a number from here to 1.5. You're either going to get 0 or 1. If you're over here, the greatest integer will be 1. And if you're over here, the greatest integer will be 0. Okay, so the greatest integer of a plus b is the greatest integer, is going to be less than or equal to, you factor out x plus y. Now, the greatest integer of theta plus theta prime, it's going to be 0 or 1. It's going to be 0 or 1. So this is less than x plus y plus 1. Okay? So this is less than x plus y plus 1. Now, we know that a is x plus theta, so that implies that 2a is equal to 2x plus 2 theta. Well, if theta is between 0 and a half, multiplying everything by 2, we get that 2 thetas between 0 and 1. So this implies the greatest integer of 2a is the greatest integer of that side, which is 2x an integer, plus the greatest integer of 2 theta, but that's 0. So you just get 2x. Now, we know that theta prime is in between a half and 1. Now, if you multiply by 2, you get 1 and 2. This tells us that the greatest integer of 2 theta is 1. It's between, this here, 2 theta, is in between 2 consecutive integers. So the greatest integer of 2 theta prime is the smaller number. Okay, so b is equal to y plus theta, which implies that 2b, greatest integer of 2b, is the greatest integer of y plus theta. Since y is an integer, we prove that it can come in front. Let me just do this correctly. Multiplying both sides by 2, we have the greatest integer of 2b is equal to the greatest integer of twice y plus 2 theta prime. The integer can come in front, and the greatest integer of 2 theta prime is 1. So it's exactly equal to 2y plus 1. Okay. So now we have to verify, now that we have everything that we need, we have to verify that what I'm writing down there is actually less than or equal to twice a greatest integer plus the greatest integer of 2b. That statement is true if and only if this statement is true. Well, that's x plus y plus x plus y plus 1 is less than 2x plus 2y plus 1. And let me write that more clearly. We know that this, which is x plus y, we know that the integer of a plus the greatest integer of b, etc., that this is less than or equal to, well, that's x, equal to x, that's equal to y, but this is less than 2x plus, that's less than x plus y plus 1. X plus y plus 1. But that equals to 2x plus 2y plus 1. And this is the greatest integer. This is the greatest integer of 2x plus that's the greatest integer of 2b. 2a greatest integer, 2b. So I did show that this is smaller than something that equals this, that equals that. That is, yep, this here is less than that. Okay. Now, case 3 is where both theta and theta prime are bigger than a half. Case 3. Theta and theta prime are between 0 and 1. That means 2 theta and 2 theta prime are in between 1 and 2. That means that the integer part of 2 theta and the integer part of 2 theta prime are both 1. Each of these are between 2 consecutive integers. That means the greatest integer of each of these is equal to the smaller number, which is 1. Okay, so we know that a is equal to x plus theta. Theta is less than 1. It's positive. So the greatest integer of a is just x. B is y plus theta prime. This is less than 1 and positive. That means the greatest integer of b is just y. Okay, so again, let's do the bookkeeping. This is x. This is y. A plus b to be determined. 2a and 2b. Now, if I add these, we get a plus b is equal to x plus y plus theta prime. The integer part of a plus b is equal to the greatest integer of that. But I can pull out the integers plus the greatest integer of theta plus theta prime. But if you add them, this is between 0 and 1. This is between 0 and 1. If you add them, you notice that theta plus theta prime is between 1 and 2. which means the greatest integer will be 1. So this is x plus y plus 1. X plus y plus 1. Okay, 2a. 2a is equal to 2x plus 2 theta. Well, that tells me the integer part of 2a, well, it's going to equal 2x plus the integer part of 2 theta. But I've already said that that's 1. So this is 2x plus 1. And due by symmetry, because theta and theta prime are both between 1/2 and 1, we're going to have 2y plus 1. 2x plus 1, 2y plus 1. Okay, so now the greatest integer of a plus the greatest integer of b plus the greatest integer of the sum is less than or equal to the greatest integer of 2a plus the greatest integer of 2b. If and only if this, which is x, plus that, which is y, plus that, which is x plus y plus 1, is less than this, which is 2x plus 1, plus that, which is 2y plus 1, if and only if, well, you have x plus x is 2x, y plus y is 2y, plus 1. And yep, that is less than 2x plus 2y plus 2. 1 plus 1 is 2. So far, both sides have the same. You add 1 here, you add 2 there. This side is now larger. It's 1 larger. So all the cases shows us the result. Combining all 3 cases, we can now conclude that the greatest integer of a plus the greatest integer of b plus the greatest integer of the sum is less than or equal to the greatest integer of 2a plus the greatest integer of 2b. In 2 of the 3 cases, just the less than, just the equal was enough. But for the third case, it was strictly less than. Okay, for the first 2 cases, you had equality. The third case, you have less than. So we can say that in all 3 cases, this is less than or equal to that. That completes this proof. That completes the proof of all 5 facts. That is, this video is done. If you like watching math like this, seriously consider subscribing to my channel. See you guys in the next video. Watch and learn.